Good afternoon, everybody. Today I'm going to talk to you about confidence bounds on freeboard at stream crossings for evaluating overtopping risk. And today my presentation will kind of follow three themes under that topic, since it hasn't been mentioned enough. Evidence of uncertainty, evaluating uncertainty, and then embracing uncertainty. So evidence of uncertainty. Typical methods for evaluating flood hazard and water surface elevations at stream crossings involve estimating a designed stream flow, typically associated with a particular probability of occurrence that is then routed through a hydraulic model, and you end up with the water surface elevation, which is a discrete water surface elevation that's then used to evaluate that structure. However, we know there's a large degree of uncertainty in what that water surface elevation might be. And that's what this figure shows. This is a cross-section. The gray area is a culvert. The red line at the top is the roadway. And the light red area is the 90% confidence bounds on what that water surface elevation might be. So you can see the large degree of uncertainty there. So that uncertainty stems from multiple factors. The three most influential of which we know are stream flow, channel and floodplain roughness, and channel capacity. So aggradation or degradation within the channel, whether it happens from natural or anthropogenic sources. Stream flow, that's putting our finger on exactly what that design flow is with the probability of occurrence. And then we have channel and floodplain roughness, which we probably all know is somewhat subjective. And even if we could take a perfect snapshot of it in time, it changes with the seasons. And so there's a need for a better approach to portray and communicate these hazards and water surface elevations that makes that uncertainty transparent. And everything I've mentioned so far assumes that the future will behave like the past. However, as Stacy mentioned in her presentation, we know there's population growth and urbanization that have resulted in land use changes in many watersheds across the nation, and this can affect the supply rate of water and sediment in many of our streams. So you can see the bottom right, that's land use change in Atlanta from 1974 to 2005. But additionally, there's mounting evidence of changing atmospheric conditions. This is a recent report from the National Climate Assessment, and the top shows an increase in the magnitude of heavy precipitation. In the bottom, you see an increase in the frequency of heavy precipitation across the majority of the United States, particularly the eastern United States, which coincides with some of the blue triangles that Stacy just showed us. So what we have is sort of this possibility of convergence of changing land use and atmospheric conditions that can result in non-stationary behavior of hydrologic response. And this can confound on that uncertainty that already exists in our model estimates. However, this is being recognized. This is a recent report or circular from the Federal Highway Administration acknowledging this uncertainty and existence of non-stationarities that we might see and that we need to account for it. And it says, we need to improve our approaches for the planning, design, and operation of transportation infrastructure. So how do we do that? How do we evaluate uncertainty? I'll present some examples today. We would do that by running hydraulic simulations in a Monte-Carlo framework. And for those of you not familiar, the way a Monte-Carlo framework works is we statistically quantify the plausible range of model inputs and parameters. In this case, discharge, channel and floodplain roughness, and aggradation and degradation. And in the cases I'll present today, aggradation and degradation is simply vertical movement of the channel bed. So we statistically quantify those. We randomly sample from the plausible range of distributions, and then we randomly sample from those distributions and route that through a hydraulic model. And then we do this a large number of times until we sufficiently sampled those statistical distributions. In this case, that's 1,000 simulations. And so we get this range of outputs or water surface elevations. You think of this as 1,000 different floods as opposed to one discrete water surface elevation, and then we can analyze those. So the example I'll present today is for McMullen Creek. This is in Charlotte, North Carolina. Drainage area of 15 square miles, 23% imperviousness. And luckily there's a stream gauge right in the middle of a 11-mile modeling reach. And you can see, there's a figure on the right, there's multiple different structure types along this modeling reach that pertain to different design stream flows or different recurrence intervals. And so the stream gauge at this site exhibits from non-stationary behavior a statistically significant increase in the annual peak flows. So estimating design stream flows usually follows under several different methods. One being a hydrologic model is used to estimate those, or you can use the USGS regression equations, or you can use at-a-site gauge information. And so the curves on this graph represent different methods for different recurrence interval events. So the yellow or the pink line at the bottom are the results from a HEC HMS model used in the FEMA regulatory flood insurance study. The USGS regional regressional curves are represented by the purple line in the middle, and the blue line in the middle represents at-a-site flood frequency analysis based on a log Pearson 3 distribution. The green curve on the top is based on some new publications, one by Sarago and Vogel, that recommend some non-stationary techniques for analyzing flood hazards based on observed trends like we see at the gauge. And so we'll look at two of these today, the HEC HMS design discharges, because that's what was in the FEMA regulatory model, and then the non-stationary flood frequency analysis, because that's what we observe at the gauge. So this is the range of model input and parameter uncertainty. And so you can see for channel floodplain roughness, aggradation, and degradation, the two cases, the distributions are similar. However, we see an increase in the non-stationary discharge distribution, which we saw on the graph. So these are the results for the stationary case, which I'll refer to from the HEC HMS design discharges. And what this graph represents, the x-axis is the stationing along the channel profile, and the y-axis is the standard deviation of water surface elevations for different recurrence intervals, the 10-year, 25-year, 50-year, and 100-year discharge. And so you can see the variation in that standard deviation along the modeling reach. So what this represents is our uncertainty and differing levels of uncertainty in what that water surface elevation might be along the channel reach. And thus, we have differing levels of uncertainty in our freeboard estimations. So what this graph represents, the x-axis is all the different structures within the model. And the y-axis represents the freeboard, or the range of freeboard, across all simulations in the Monte-Carlo analysis. And so the negative values indicate that the water surface elevation exceeded the low chord of the structure. We're calculating freeboard based on the low chord minus the water surface elevation. And so you can see the different ranges here. And the main point to take away from this is we have different confidence in what our predictions might be throughout the landscape. Our uncertainty is variable. So there's hidden risk in certain locations that's greater than others. But not all these pertain to a 50-year design event, which is what's represented here. So we'll zoom into this particular structure just to look a little closer, and this is what it looks like. It's a double opening box culvert on a principal arterial urban state highway. So this is the distribution of freeboard across different design stream flows. And you can see, particularly for the 50-year stream flow indicated by WSE, or water surface elevation 50, that most of those simulations fall above the zero freeboard, and that the mean indicated by the black line is about 1.5 feet, which was probably what was designed for. But we can look at this from a probabilistic standpoint. The black dot representing the elevation of the low chord, the orange dot representing structure overtopping. And so what this basically says, 75% of the simulations do not exceed the low chord. So we're 75% likely not to exceed the low chord. And then there's a much lower likelihood of overtopping. And so we can view this, we want to know, well, how much exactly is our uncertainty? What might be the water depth over the structure? And this is the figure you viewed earlier with the gray area representing the culvert, the red line, the roadway. And you can see the red indicating our 90% confidence intervals. And so the top of the roadway kind of falls out of that range, so there's a low probability it'll be overtopped. But the maximum simulation we observe says there might be a foot of water over the roadway. And then we can also see around our freeboard or our water surface elevation, there might be, like with a 90% confidence interval, there might be plus or minus 4 foot in that. So we know exactly how much our uncertainty is. However, for the non-stationary case, we can see a large increase in exceeding the freeboard. Not even for the 50-year storm, but for the 25-year, not storm, stream flow, for the 25-year stream flow as well. So we compare these probabilistically, and we can see that the low chord in the non-stationary case is exceeded approximately 75% of the time. So there's a 25% chance that that will be exceeded. And there's a 60% chance that overtopping will occur in the non-stationary case. And so, again, we can view how much is this uncertainty. And now our sort of zone of uncertainty, our 90% confidence interval, if you will, falls in our structural overtopping. And this is about 1.5 feet in this case. But we could tailor this to our different appetites for risk. So we could say, well, you know, I'm a little more risk prone or risk adverse. Maybe I'll shrink this to 30 to 70% chance likely to be inundated, and we could look at that as well. But knowing, you know, how much this uncertainty is and what the possible depth might be over the roadway, we can consider the likelihood of our design stream flow occurring over the service life of the structure. And so these are, you know, well-known equations in the literature and publications. So the LRFD specifications call for a 75-year design life. And so we can see there's a 78% chance that's a 50-year stream flow will happen over 75 years if that's the service life of the structure. So we can take that into consideration. And if the design stream flow does occur, you know, we can compare the probabilities with our discrete estimation. This is from the regulatory model. I'm not saying, you know, this is what the design used when they built this structure, but, you know, it provides a good example of comparing a discrete realization with a range of events. And so you can see that in the stationary case, 50% of the simulations exceeded that discrete water surface elevation. In the non-stationary case, 90% of the simulations exceeded that discrete case. So it just emphasizes considering this range. So what do we do with all this? We still have to build our structure. We still have to set our roadway elevation and set our load chord. So we need to embrace this uncertainty rather than you know, being daunted by it. And so we can begin by quantifying it and thinking, you know, what's the consequence if we're wrong, and what is the range of uncertainty? For more grave consequences and higher uncertainty, we need to perform more rigorous analysis. For, you know, lower consequence situations and less uncertainty, we can kind of tone our analysis down and maybe go with something like sensitivity analysis. And there's existing guidance on this. For instance, the circular that I mentioned earlier, it provides equations and methods for estimating confidence bounds in stream flow or design storms. It also provides guidance on how to deal with non-stationarity and how to identify that. And it provides different levels of analysis associated with different uncertainties. So this is a good documentation that can be used. So if we do this, we begin to you know, evaluate things over a range of events rather than a discrete value. And we can start to consider the consequences across that range. And so we can maximize our operating space over which the structure is serviceable, so that if our design event is met or exceeded, there's not complete deficiency or loss of service of the structure. We still have some level of service there. And so we can begin to incorporate what's been termed graceful failure in that analysis. So the approaches presented here make uncertainty in freeboard estimates transparent and consider the influences of changing land use and climate through time. By doing so, we can identify locations of elevated or hidden risk that might not otherwise be identified by these discrete evaluations of water surface elevations. And so these methods provide a way to design infrastructure with more resiliency and provide a better method for communication and decision making. With that, thank you, and we'll take time for any questions.
So there's plenty of time for questions.
I don't think I need a microphone, but
Okay.
so when you did your Monte-Carlo analysis, you assumed like a normal distribution for a lot of the variables.
Right.
Do we know that, or we're just kind of choosing that because that's like an easy one?
Yes, for certain things, we do know that. So like, if you notice for discharge, it followed a log normal distribution. And so that's known the methods used to calculate sort of that range of uncertainty followed some guidance methods by the USGS that it follows a log normal distribution. For channel change, that was an empirical analysis, so it was able to directly evaluate that distribution. For roughness, things get a little bit more fuzzy. People have used different things from a uniform distribution, which assumes equal likelihood of sampling across all plausible ranges. Here I use a normal distribution just to kind of place a little more emphasis on the mean. But yeah.
Questions? Okay, well, thank you very much.